Welcome to the video help with physics problems for Physics 1B. In this video we're going to be covering homework set 5, part 1, which is everything under the headings interference and diffraction, diffraction limits of resolution, and gratings and spectra. For 1221 students this is questions 1 to 6. For 1231 students this is questions 1 to 8. Problem 1. This is a 1, 2, 3, 1 only problem. Part A of this question asks how many complete fringes appear between the first minima of the fringe envelope on either side of the central maximum for a double slit pattern if lambda is equal to 550 nanometers, D, which is the spacing between the slits, is equal to 0.150 millimeters, and A, which is the slit width, is equal to 0.030 millimeters. So what's going to happen is the image we're going to see is going to be the double slit interference pattern imposed over the top of the diffraction around the single slit. So what we'll end up with is the single slit pattern, which will look something like this. And over inside this central envelope and these other fringes, we'll have our double slit fringes, which will be like this. So the single slit will determine where these first minimums are. These minimums will satisfy the equation A sine theta is equal to 1 times lambda. That will give us the theta at which this minimum and this minimum occurs. And then what we need to do is count up how many of these maximums from the double slit occur within that. So let's solve this and work out where these minimums are. We know that sine theta is equal to lambda, which is 550 times 10 to the minus 9, over A, which is 0.030 times 10 to the minus 3. So that tells us that sine theta is equal to 0.0183 with a repeater. So these threes keep on going. So that's the sine theta. Now what we need to do is work out how many of these maximums occur for thetas less than this sine theta. So to do that, we know that d sine theta is equal to n lambda, tells us how many maximums occur in a double slit pattern. So what we're going to do is solve this for n. So n is equal to d sine theta over lambda, which is equal to 0.150 times 10 to the minus 3 times sine theta, which we've got over here, 0.0183 repeater, over 550 times 10 to the minus 9. Solving that, we end up with 4.9999. Okay, so now the question asks how many complete fringes will we see? So this will be the n equals 0, and then we'll have n equals 1, n equals 2, n equals 3, n equals 4, and n equals 5 will be directly over this minimum. So we're not going to see this one because it's at a minimum. So we'll see 1, 2, 3, 4, and then the central one on this side, and then the other 4 on this side. So 4 plus the central one, which means that we will see 9 fringes. And that's complete fringes. Now part B of this question says, what is the ratio of the intensity of the third fringe to the side of the centre to that of the central fringe? So to do this, we're going to need to use our intensity equation. To get the intensity when we're considering the diffraction with a double slit, we need to put together the intensity equations for a single slit diffraction pattern with the double slit interference pattern. So both those formulas are given on your formula sheet, but you need to put them together. So what we have is the intensity is equal to I max times cos squared pi d sine theta over lambda. This tells us the intensity of a double slit pattern, and then we need to put in the intensity of the single slit diffraction pattern, which is given by sine beta over 2 over beta over 2 squared, where beta is equal to 2 pi a sine theta over lambda. Okay, so let's just start by working out what sine theta is. We know this is the third maximum, so we can use this equation here and substitute in n equals 3. So we have sine theta is equal to 3 lambda over d. Okay, so let's just work out what beta is for a start. Beta is equal to 2 pi a times sine theta, which is 3 lambda over d, and then this is all over lambda. So these lambdas will cancel out, and we'll end up with 6 pi a over d. So this is our beta, and let's just look at what happens inside this cos. We have, let's call this alpha. And alpha is equal to pi d over lambda times sine theta, which is 3 lambda over d. So these d's cancel, and we end up with alpha is equal to 3 pi. So let's now substitute these in. The intensity at the third fringe will be equal to I max, that's the central intensity, the intensity here, times cos squared 3 pi times sine of beta over 2, so that's sine of 3 pi a on d over 3 pi a on d, and this is all squared. So solving this, we've got I max cos squared 3 pi. Cos of 3 pi is minus 1, squaring that we've got 1, and 3 pi a on d is equal to, substituting in 0.03 here and 0.15 here, we don't have to convert from millimeters because we're dividing, we get 1.8849 when we solve that on the calculator. So we've got sine of 1.8849 over 1.8849 all squared, and then solving this on the calculator we end up with I max times 0.255. So our answer is 0.255 times the maximum at the central fringe. This is problem 1 for 1221 or 2 for 1231. In this problem we're given a diagram and we're told that lambda is equal to 440 nanometers. We're told that the light passes through a double slit setup, and this diagram shows us the intensity versus the deflection angle in degrees. This angle here is 5 degrees. And we're asked in part A to calculate the slit width. So the slit width, we can work this out by looking at where this first minimum in the diffraction pattern occurs, because the slit width is what's responsible for the diffraction part of this. So the diffraction minimums are given by the formula A sine theta is equal to n lambda, or m if you want. And this is the first minimum, so this is m equals 1. So we've got A is equal to lambda over sine theta. And you can see on the diagram that the first minimum occurs at approximately 5 degrees. So we've got that the slit width is equal to 440 times 10 to the minus 9 over sine of 5 degrees. So solving that on the calculator, making sure that the calculator is in degrees, you end up with 5.048 times 10 to the minus 6. So this is equal to 5.0 micrometers as the slit width. Now part B asks us what's the slit separation. The slit separation is D, so we have to use the formula D sine theta is equal to m lambda. So this first maximum here, this is the m is equal to 0, and then we've got m is equal to 1, m is equal to 2, m is equal to 3. Now you can see the m is equal to 4 maximum is going to be here. There's no maximum there because it's at the minimum of the diffraction pattern. So we have m is equal to 4 here. So m equals 4 corresponds to 5 degrees. So substituting that in, we've got d is equal to 4 times 440 times 10 to the minus 9 over sine of 5 degrees. Now this is going to be 4 times as big as this, so we'll end up with 20 micrometers, which, this will be useful later, this is equal to 4a. Okay, now part C says verify the displayed intensities of the m equals 1 and m equals 2 interference fringes. So we need to verify this intensity here and this intensity here. The maximum intensity, the graph says, is equal to 7. We need to use the formula for when we have a diffraction pattern and an interference pattern. So to do that, we combine the two formulas on the formula sheet, and we end up with the intensity is equal to the maximum intensity times cos pi d sine theta over lambda, and this is cos squared, and then we need to times that by sine beta over 2 over beta over 2, and this is all squared, where beta is equal to 2 pi a sine theta over lambda. And let's refer to this as alpha. So let's start by solving for the m equals 1 case. When m is equal to 1, that's this one here, we have, using the formula for interference fringes, sine theta is equal to m lambda, which is 1, so that's lambda over d. So now what we can do is we can substitute this sine theta in and find alpha and find beta. So this tells us that alpha is equal to pi d on lambda times sine theta, which is lambda over d. So this is equal to pi. And beta is equal to 2 pi a over lambda times sine theta, which is lambda over d. These lambdas will cancel. Now let's replace this d with 4a. So these a's cancel and we end up with pi on 2. So now we can substitute this in to get that intensity. So we've got I is equal to I max cos squared pi. So this will be minus 1 squared, which will just be 1 times sine of pi on 4 all over pi on 4 squared. So solving that on the calculator, we end up with 0.81 times I max. And then the I max we said was 7 approximately, so this should be approximately equal to 5.7. And if we look at this, you can see this is approximately 5.7, that's just below the 6. So that one is correct. Now we were also asked to verify it for the m equals 2. So when m equals 2, let's make some more space, we've got sine theta is equal to 2 lambda over d, which tells us that alpha is equal to lambda d on pi times 2 lambda on d. So this is equal to 2 pi. And beta is equal to 2 pi a over lambda sine theta. So that's 2 lambda. And instead of d, let's put 4a. So these numbers cancel, the a's cancel, the lambdas cancel, and we end up with beta is equal to pi. So our intensity is equal to the maximum intensity times cos squared of 2 pi. So this will just be 1 squared times sine pi on 2 over pi on 2 all squared. And so solving this on the calculator, we end up with 0.405 times I max. And then substituting in the 7, we end up with 2.8. And looking at the intensity here, you can see it's just below 3, so that looks reasonable. So we verified those two intensities. This is problem 2 for 1221 or 3 for 1231. In this problem, you have two car headlights that are 1.23 meters apart. And the question asks us, at what maximum distance will the human eye be able to resolve these? And we're told that we can assume that the human eye is a circular aperture with a diameter of 5 millimeters. So to answer this problem, we're going to need to use Rayleigh's criteria. Which says that to resolve two sources, the central maximum of 1 falls on the minimum, on the first minimum of the other. This gives the limiting case. So this gives the closest two sources can be in order for us to resolve them. So this gives us the formula. The minimum angle between the sources is 1.22 lambda over d, where d is the diameter of the aperture. The 1.22 comes about because it's actually a circular aperture, not just a single slit, and the lambda is the wavelength. So we'll just need to use this equation to work out the solution to this one. So we've got that the minimum angle between these two sources is 1.22 times 550 times 10 to the minus 9. That's the wavelength, which we're told in the question, and d is the 5 millimeters. So solving this, we get 1.342 times 10 to the minus 4 radians. This is the minimum theta here. And what we want to know is this distance, let's call it x, of the lights from the eye. So we can write from this tan of theta min on 2, so that's considering this triangle here, is equal to the 1.23 on 2 over x, and then tan theta is approximately sine theta, which is approximately theta, so this is approximately theta min on 2, so these 2's will cancel out, and we have x is equal to 1.23 over theta min, where here's our theta min here, so we're just substituting that in. When we solve that on the calculator, we get 9.2 kilometers. So we should be able to resolve these headlights when they're 9.2 kilometers away. Okay, now we're going to do problem 3 for 1221 or 4 for 1231. This problem, part A, states how small is the angular separation of two stars. So we've got two stars, and we want to work out their angular separation here, theta, if their images are barely resolved by a telescope with a lens diameter of 76 centimeters, so 0.76 meters, and a focal length of 14 meters. And we're told we can assume lambda is equal to 550 nanometers. Well, we'll need to use the Rayleigh criterion again. The minimum separation they can have and be resolved is given by 1.22 lambda over d. And so this is equal to 1.22 times 550 times 10 to the minus 9 over 0.76. And solving this on the calculator, we end up with 8.8 times 10 to the minus 7 radians. Now part B says find the distance between these barely resolved stars if each of them is 10 light years distance from the Earth. Okay, so let's call this distance between them x. This distance here is 10 light years. And we've got a right angle triangle here with theta min on 2. So we have sine theta min on 2 is equal to opposite, which is x, over the hypotenuse, the 10 light years. Now the distance between them is 2x, because each of these is x, it's symmetric. So what we're trying to find is 2x. Now to make it easier, let's use the normal approximation. Sine theta, because theta is small, is approximately sine theta min on 2. So we have 2x is equal to theta min times the 10 light years. And now all we need to do is substitute in. So we've got 8.8 times 10 to the minus 7 times the 10 light years. Now that's 10 times the speed of light, which is 3 times 10 to the 8, times the number of seconds in a year, which is 365, which gets it into the number of days, times 24, the number of hours, times 60, the number of minutes, times 60, the number of seconds. So solving this on the calculator, we end up with 8.4 times 10 to the 10 meters. So that's the separation, that's 2x, the distance between these two stars. Now part C, for the image of a single star in this telescope, find the diameter of the first dark ring in the diffraction pattern as measured on the photographic plate placed on the focal plane. Assume that the star structure is associated entirely with the diffraction at the lens aperture and not with the small imperfections. Okay, so what we've got here is the light coming through our aperture. Theta min gives us the angle between the central maximum and the first minimum here, and the distance between our aperture and our focal plane is 14 meters. So we'll be considering this triangle here, and what we'll actually want to get is the diameter. So this here is the radius, and we'll need to double it to get our diameter. So we have tan theta min, which is approximately theta min, is equal to r over 14. We know from our Rayleigh criterion that theta min is equal to 1.22 lambda over d. So this tells us that the radius is equal to 14 times 1.22 times 550 nanometers over the diameter, which is 0.76. So solving this, we end up with 1.236 times 10 to the minus 5, which tells us that the diameter, 2r, is equal to 2.5 times 10 to the minus 5 meters. So that gives us the diameter of the first dark ring. Okay, we're on to problem 4 for 1221 or 5 for 1231. In this problem, we've got a ruby laser with a wavelength of 694 nanometers. It goes through a circular aperture with a diameter of 2 centimeters. Now we're told that this is aimed at the moon and that we can assume that the spread is due only to the diffraction of this aperture. So we've got on our moon theta min here, and it's a distance of 380,000 kilometers from the Earth. And so we can get the radius of our beam here, the distance between the central maximum and the first minimum, if we can work out theta min. Now, the theta min is going to be determined by the Rayleigh criterion. So we have theta min is equal to 1.22 lambda over d. So this is equal to 1.22 times 695 times 10 to the minus 9 over 0.02. So solving that, we get theta min is equal to 8.83 times 10 to the minus 7 radians. So now we can use tan theta min is approximately theta min. Using the geometry here, that is equal to the radius of the beam over 380,000 times 10 to the 3. And so substituting in, solving this for the radius, we get that the radius is equal to 16 kilometers, but we've been asked to find the diameter, so the diameter is double that. It is equal to 32 kilometres. This is problem 6 for 1231 only. In this problem, we're asked to prove the expression I is equal to 1/9 I max 1 plus 4 cos phi plus 4 cos squared phi, where phi is equal to 2 pi d sine theta over lambda for the intensity pattern for a 3-slit grating. So that's a grating with 3 slits, 1, 2, 3. And we're considering the intensity at some point on the screen P here. We're told that we can assume that D is a lot less than lambda. D is the space between the adjacent slits, so this is equal to D. So we consider the light rays travelling to P. Now this angle here is given as theta, and so this angle up here is theta, and so the light rays from the second slit have travelled an extra distance d sine theta, and the light rays from the third slit have travelled a further distance d sine theta. So the difference between the light from 1 and 3 is 2d sine theta. Now we can write an expression for the electric field arriving at point P due to each of these different slits. So we've got that the light through slit 1 is given by E naught sine omega t minus phi, and then E2 is equal to E naught sine omega t, and E3 is equal to E naught sine omega t plus phi. Now phi is dependent upon the path difference between these 3 parts. The difference between the distance travelled from point 1 and point 2 is the same as the distance travelled from point 3 and point 2, only in the opposite direction. Point 3 has to travel an extra distance of d sine theta, and point 1 travels less by d sine theta. So that gives us the minus phi up here and the plus phi down here. And so the optical path difference is equal to d sine theta. That's just what we've said here, the d sine theta. And so this tells us that the phi is equal to d sine theta over lambda times 2 pi. So this is getting it into radians. This tells us what fraction of a wavelength this optical path difference is. So now we can use the rule of superposition to add up all the contributions of the electric field at P. All we need to do is sum these together. So we've got that the electric field at P is equal to E naught, that's a common factor, sine omega t minus phi plus sine omega t plus sine omega t plus phi. And what we're going to do now is use the mathematical relationship sine A plus sine B is equal to sine A plus B on 2 cos A minus B on 2, and this is all times 2. So we'll call this one A and this one B. So we've got EP is equal to E naught. Now we've still got this sine omega t, and this sine A plus sine B becomes plus 2 sine. Now when we add A and B, we get 2 omega t divided by 2, so this is omega t, times cos of the A minus B, so that's 2 phi on 2, so that's phi. So we can write this as E naught sine omega t outside of 1 plus 2 cos phi. And so the maximum value, E max, will equal E naught sine omega t times 3, because the maximum value this can have is 3. Now what we're asked about is the intensity, and the intensity is proportional to the electric field squared. So we have that EP squared is equal to E naught squared times sine squared omega t times the square of this. When we square this, we get 1 plus 4 cos phi plus this squared, which is 4 cos squared phi. We can rearrange this equation here to tell us that E naught sine omega t is equal to E max on 3. And so we can replace this with E max squared on 9 times 1 plus 4 cos phi plus 4 cos squared phi. And E max squared is just I max, so this is equal to the maximum intensity over 9 times 1 plus 4 cos phi plus 4 cos squared phi. And that, as you can see here, is what we were asked to show. Okay, this is problem 5 for 1221 or 7 for 1231. So in this problem, we're told that light with a wavelength of 500 nanometers, so that's 500 times 10 to the minus 9 meters, is normal incidence on a grating with 6 times 10 to the 5 rulings per meter. So we've got 6 times 10 to the 5 rulings per meter. And we're asked to find the angles for all orders of diffraction for this wavelength. So in order to do this, we're going to need to use our diffraction grating equation. We're going to need to use d sine theta is equal to m lambda. Now in this equation, d is the distance between the rulings. So we've got the number of rulings per meter. D is actually equal to 1 over the number of rulings per meter, and so it's equal to 1 over 6 times 10 to the 5, so that is equal to 1.667 times 10 to the minus 6 meters. That tells us how far between adjacent rulings. Okay, and what we're trying to work out is theta, so we can rearrange this, and we've got sine theta is equal to m lambda over d. And so m, that's an integer, m tells us the order. So we've got 500 times 10 to the minus 9, that's our lambda, times m over the spacing between, so that's 1.667 times 10 to the minus 6. Solving this, we end up with 0.3 m, so that's what sine theta is. And we're asked to find theta for all the orders that we can see. Okay, so if m equals 1, then we've got sine theta is equal to 0.3, and solving that on the calculator, we end up with theta is equal to 17.5 degrees. If m equals 2, we've got sine theta is equal to 0.6. Solving that one on the calculator, we end up with theta is equal to 36.9 degrees. If m equals 3, we've got sine theta is equal to 0.9. Solving this on the calculator, we end up with theta is equal to 64.2. And then if we try m equals 4, we end up with sine theta is equal to 1.2. But that's a problem because sine theta can only go between 1 and 2. So we don't actually get anything for this fourth order. So the only ones that we can see are the first, second, and third, and we've found those angles now. Okay, this is problem 6 for 1221 or 8 for 1231. And in this problem, we're told that sodium light contains 2 wavelengths. We've got one wavelength, which is 589.0 nanometers, and then a second wavelength, which is very close and equal to 589.6 nanometers. Well, that should be an NM. And this light is allowed to shine at normal incidence on a grating with 40,000 rulings spread over 75 millimeters. So we've got 40,000 lines in 75 millimeters. So let's start by working out the spacing between our rulings. So that's going to be equal to 75 millimeters, so 10 to the minus 3, over the 40,000 lines. And solving that on the calculator, we end up with 1.875 times 10 to the minus 6. And that's meters between each of these lines. And we're asked, find the angular separation of these lines in the first 3 orders. So what we need to find out is, well, what's the difference in angle that these two very similar wavelengths make as they go through the grating. So to do that, we're going to need to use our grating formula. M lambda is equal to d sine theta. But what we're actually looking for is a separation. So we actually want d theta. So there's a little mathematical trick we should use here. Let's rearrange this to make lambda the wavelength, the subject. So we've got d sine theta over m. And then we want to know, well, how does the angle change as the wavelength changes? And in order to do that, we're going to need to differentiate. So we can write d lambda d theta, differentiating this with respect to theta, and you know that that's equal to d cos theta over m, because you're good at taking derivatives of things such as this. And so this equation we can rearrange, and this tells us that the angular separation d theta is going to be equal to m d lambda over d cos theta. So this is the equation that we're now going to have to solve, because it's d theta that we're trying to find for the first 3 orders. So the first 3 orders are when m is equal to 1, 2, and 3. Okay, so d lambda, that's the separation between the wavelengths. So that's lambda 2 minus lambda 1. So that's equal to 589.6 minus 589.0 nanometers. So that's going to be 0.6 nanometers. So we know m, we know what d lambda is. We've calculated d up here. So we just need to work out what cos theta is. Well, we can get sine theta from this. These wavelengths are almost the same here. So if we want to get sine theta, we can rearrange this equation. Sine theta is equal to m lambda over d. For the first one, we've got m equals 1, so that's lambda, and this isn't the difference in wavelength, this is the wavelength. So we'll just take the average wavelength, it doesn't actually matter. So we'll take 589.3 nanometers over 1.875 times 10 to the minus 6. So remember, nanometers is times 10 to the minus 9. Okay, and this is equal to 0.31429. But what we needed up here was cos theta. So once we've got sine theta, you can either work out what theta was and then plug it into cos to get it, or you can remember that sine squared theta plus cos squared theta equals 1. Either way, solving for cos theta, we end up with 0.9493. So now we've got everything that we need to substitute in this equation when m is equal to 1. So we've got d theta, well, this is m equals 1. We've got d theta is equal to 1 times d lambda, which is 0.6 times 10 to the minus 9, over d, which was 1.875 times 10 to the minus 6 times cos theta, which is 0.9493. And solving that one on the calculator, we end up with 3.37 times 10 to the minus 4 radians. And if we want, we can convert it to degrees, which is 0.0193 degrees. Okay, now when m equals 2, you'll notice when m equals 2, sine theta is different as well. Instead of having a 1 here, we have a 2, and so it's actually double what this one is. So we end up with sine theta is equal to 0.6284. It actually ends up 6286. And then we can solve for cos theta, and cos theta is equal to 0.7778. Again, we can just use cos squared theta plus sine squared theta equals 1 to solve for that. And then that tells us that d theta is equal to, so now we've got 2 times 0.6 times 10 to the minus 9 over 1.875 times 10 to the minus 6 times 0.7778. And solving this one, we end up with 8.22 times 10 to the minus 4 radians, which is equal to 0.047 degrees. And finally, m equals 3. So in this case, sine theta is equal to 3 times lambda over d. And so it is equal to 0.9429. And so cos theta is equal to 0.3330. And then d theta is going to be 3 times 0.6 times 10 to the minus 9 over 1.875 times 10 to the minus 6 times 0.3330. And solving that, we end up with 2.88 times 10 to the minus 3 radians, which is equal to 0.165 degrees. Okay, so that's how we solved that problem.